Welcome to part 2 of the problem-solving session for Chapter 8. We begin where we left off at question 4. Okay, here we are told that the launching mechanism of a pop gun consists of a spring constant, which is to be determined, and when the gun is fired vertically upward, the spring is compressed by 0.12 meters and a projectile of 0.035 kilograms is projected upward to a maximum height of 20 meters above the relaxed position of the spring. Determine the spring constant K, neglect all other forces. Now here is an interesting situation that I would like to point out to you. Our book actually considers point B to be the reference position so that they take y sub b to be equal to 0 and measure all distances from here, negative if they are below or positive if they are above. How about if I suggest that we might do the following? What if we let position A, or y sub A, equal 0, y sub B then would equal 0.12 meters, and y sub C would equal 20.12 meters. In other words, we make an adjustment of our 0 to coincide with point A, allow point B to be 1.2 meters above the 0, and position C to be equal to 20 plus 1.2 meters. This is one way that we can solve the problem, even though the book does not do this. Now, the other thing that I'd like to point out about this problem is that we are going to have not only gravitational potential energy, in other words, we are going to have values of delta UG, but we also have spring potential energy, as well as kinetic energy, since our projectile will be moving. So this is a situation here where all three terms will become important. However, what is absent is the resistive forces, or in other words, the work done by non-conservative forces. So energy will be conserved and will be sloshing back and forth between the kinetic and the potential. So let's agree, just to have a different perspective in this problem, that we will say that at position A, we have the following. We have our 0 reference of potential energy. X sub A, however, is compressed because here this is the, this is 0, excuse me. X sub A is 0.12 because the spring is compressed from its relaxed position, which is X sub B at the point B. And the spring, the little projectile starts from rest, so K sub A is equal to 0. After all, it's pushed up against the spring. At position B, we'll take y sub B to be equal to 0.12 meters, okay? We'll take x sub B to be equal to 0. Now the spring is relaxed. And K sub B, K sub B will be something for which we do not know. Position C will have the following properties. Y sub C is equal to 20.12 meters. X sub C is, of course, 0. The spring is already relaxed. And K sub C, since the pop gun reaches its maximum position, will be equal to 0 as well. In other words, V sub Y at the maximum height is equal to 0. So armed with that, let's see what we can get. Well, we know that. Let's look at the differences between A and B. So from A to B, this is what we have. All right. We've got a delta K BA plus a delta U sub G BA plus a delta U sub S BA, S for spring constant, no non-conservative forces, so that gives us 0. Let's see, KB, and remember we're solving for the spring constant, KB minus KA, KA equals 0, plus UG at B, 0, minus UG at A. Oh, I'm sorry, this one's not 0. Uh-oh, mistake. Let's use our eraser right here and rewrite this, because remember that UG sub B, we allow Y sub B to equal to 0.12 meters, but this is certainly equal to 0. Plus US sub B minus US sub A equals 0, and here US sub B will equal 0. So we've got KB is equal to, let's see, minus UG sub B plus US sub A. In other words, minus mgy sub b plus 1/2 kx sub a squared. Now look at this. We have the kinetic energy at point B, okay, when the mass or projectile is first released, and we have the spring constant, which is what we're asked to solve. We have, in other words, two quantities which are unknown within one equation. We need a second equation to contain the same unknowns to eliminate one of these unknowns. And no problem, we consider the motion of the pop gun, or the energy transformations that occur of this little projectile between positions B and C. So let's see. We have a delta K CB plus a delta UG CB, and note that delta US CB is 0 because we're going from relaxed state to relaxed state, so we eliminate that altogether. Now, K sub C minus K sub, oops, lost my pencil, minus K sub B, of course we know K sub C is 0, is plus UG sub C minus UG sub B equals 0. So let's see. KB, we already have solved for. So minus KB will give us minus mgy sub b. Remember here we had a minus sign, so we mustn't forget that. This will become positive mgy sub b plus, now this becomes negative, minus 1/2 kx sub a squared. That's this term right here, okay, which we've substituted, plus UG sub c, which is mgy sub c, minus UG sub b minus mgy sub b equals 0. Okay, well look, mgy sub b here minus mgy sub b here, these will fall out, and so here we see that 1/2 kx sub a squared, of course it was negative, but we're going to take it to the other side, equals mgy sub c, solving for k, we get k equals mg y sub c divided by 1/2 x sub a squared, and that should give us, let's see, remember that y sub c is 20.12, not 20, but 20.12. Solving for the numbers here, we should get something like 58.5 newtons per meter. And you can verify that using your calculator, plugging in the value of m, which I'd have to go back and check each of these numbers. Remember, y sub c you're going to use as 20.12, and 1/2 x sub a. X sub a is, of course, x sub a squared is 0.12 squared. Okay, so we've managed to solve this problem by looking at the increments between A and B, and then B and C. And the only reason we had to do this twice is because we ended up with two unknowns in the same equation. Let's move on to the next problem. Oh, actually, let me go back, and one thing that I forgot is that we actually have an animation, and it may be very nice to see this animation. Let's go ahead and adjust our spring compression here to match the quantity which was given to us, 0.12. Let's see, 0.12. Oops. There we go. 0.12, which was our initial spring compression. We have, let's see, what do we want? The height of the projectile will be 20. I don't know if I can change these numbers. Nope, they're not going to let me change these numbers. But let's see, when our projectile gets to 20.12, let's see, oh, in fact, we can adjust for the spring constant, what we just solved for, and that way we can actually solve for the number. So let's take the spring, the largest value we can get is 955. So that's not very good, but anyway, let's work in with these numbers. Let's see what we get. So let's fire our projectile. And what do we see? The highest speed of the projectile, in fact, well, we haven't learned very much here. We'd have to solve for the speed of the projectile when it's at when the spring is in the relaxed state. In other words, V sub B for us. So this should, if we take this with our spring constant, which of course here is 955, but the value that we just obtained, we should be getting a value for V sub B, which we can match with this. So in fact, this animation is actually not very helpful to us. Let's see. Again, if we compress further, fire, and you can see the speed just at the launch, and the fact that the projectile is going to reach a height here of several meters. Here, our spring compression. Let me see this again. If we have 0.12, for some reason we're not getting the height of the projectile. Anyhow, the next problem, question 5, says a block which is initially at rest is pulled to the right along a horizontal surface by a constant force of 12 newtons. The surface is rough and has a coefficient of kinetic friction, which is equal to 0.15. What is the speed of the block after it has moved 3 meters? Now here we have to be careful because we have friction, and therefore, and not only friction, but we are also given a second force. So we have a force of 12 newtons, which is applied in the positive I hat direction, okay, newtons here. We have the force of friction, which we are going to take to be against the direction of motion, and that will be given by mu k, the coefficient, which by the way is what was given here, not the force of friction, times the normal force, and this force of friction should be in the minus I hat direction. Okay, now we seem to have lost a diagram here, so let's go ahead and see if we can't draw our block on the horizontal surface. It's going to have the force of gravity acting on it, mg. There will be the force of support from the surface, n, the normal force. The pulling force is F in the direction of motion, which we will take to be delta R, in other words, to the right, and friction to the left, opposing the motion. Now, you can see here by Newton's second law that N, if we look at the free body diagram, which I'm not going to draw, but I'm sure you know, the forces in the y direction equal 0, N minus mg equals 0, so N is equal to mg, which means that the kinetic force will be minus mu k times mg in the I hat direction. Now, why do we need to know these forces? Because we know that Fg is conservative and therefore stores potential energy, Ug. Fs is conservative and therefore stores U sub s. But F itself we cannot assume is conservative, and certainly we know the kinetic friction is not conservative. So what we have to do here when we relate the motion of this mass is that we must consider delta K plus delta U, which by the way will not change gravitationally speaking, nor will spring, because there is no spring anyway, but that the change in kinetic energy comes strictly from the work done by the non-conservative forces. So K final minus K initial, or KB minus KA, however we want to write it, it doesn't matter, is a result of the work done by F as the block is displaced delta R, plus the work done by F sub K as the block is displaced delta R. In other words, we have two forces, non-conservative, which are doing work on our mass. Okay, well, our mass starts from rest. So we have a we have initial kinetic energy, which is equal to 0. Okay, it gets pulled to the right, and of course this force is what initiates the motion to do work. However, it's friction which is going to reduce the energy that this mass would otherwise have if it was only having positive work done, because friction will do negative work. So 1/2 mv final squared is equal to, let's see, delta R is in the direction of F, so the scalar product here will be positive. In other words, positive work is done, 12 newtons times 3 meters times the cosine of 0, which is, of course, positive 1, plus the work done by kinetic friction, which is, let's see if we can get a value here. If we take mu k times mg, we should have a value of 8.82 newtons, and please verify that this is the case, times 3 meters, but because the angle between friction and the displacement is 180, we have, of course, negative work being done. So, 1/2, here, let's see if we can go ahead and get some numbers, and then we'll solve for B final. We've got 36 joules of positive work done by the force, minus 26.5 joules of work done by kinetic friction, giving us a net value of 9.54. If I read my, 545. Okay, we can go ahead and put that there. And so when we solve for V, okay, V final is going to be equal to the square root of 2 times the work done by the conservative forces here, divided by the mass, which is 6 kilograms, and that should give us a value V final, which is 1.78 meters per second. Notice that if friction was not doing work, we wouldn't be subtracting this term, and therefore we would have a much greater velocity or a much greater change in kinetic energy at the end of the work being done by this force. Okay, let's go to the next problem. Here we are told that there is a block which has a mass of 0.8 kilograms right here, and this is moving at a speed of 1.2 meters per second when it initially makes contact with a spring. And this is actually before the spring is even compressed. Okay, so we don't know what the velocity was at point A, but what we do know is that it has a velocity of 0.12 meters. So let's call that V sub B, okay, the velocity at point B, when it collides with a spring that has a spring constant of 50 newtons per meter. And we're told, suppose there is kinetic friction between the block and the surface. So in other words, from here to here, we know there is kinetic friction, which is equal to mu k times n. But of course, here again, free body diagram of the block, we've got mg downward, we've got normal force supporting it, we've got kinetic friction opposing the motion, and we have a spring force, in other words, a spring force which tries to push outward on the spring as the spring gets compressed, the spring force tries to oppose that, and so is applied in this direction as well. Okay, so F sub S, the spring force is in this given direction. But the motion of the block is to the right. Okay, so this is a situation here where we've got a non-conservative force and a conservative force doing work on this block. In fact, the result of the conservative force doing work is to store potential energy. Okay, store potential energy as the spring becomes compressed. Anyhow, from the free body diagram, we can clearly see that N minus mg equals 0, N equals mg, and so here the kinetic friction will be mu k times mg. All right, so let's go ahead and use the energy approach here. So we've got delta K from C to B, C being the position where the spring is fully compressed and the mass momentarily stops, plus no change in gravitational potential energy because this is a horizontally moving block. So delta U sub G is 0, but we do have spring compression, so we have a delta US C to B, equaling the work done by the non-conservative force, which is, of course, friction. Okay, Kc minus Kb, Kc equals 0, the block momentarily stops, plus Us sub C minus Us sub B. Well, at position B, we have a situation in which the block, the spring, is relaxed, it hasn't been compressed, and so there should be no spring potential energy. But this should equal Fk dotted with delta R. Now here again, you can see that the work that will be done will be negative since delta R is to the right, while the spring force, the kinetic friction is to the left, and so opposes that. And so the angle between delta R and F sub k is -1. Okay, let's see. So minus K sub B minus, let's start here, minus K sub B plus US sub C equals minus mu K mg times delta R. Okay, minus a half mvb squared plus 1/2 k x sub b squared, sub c, this is the point C, equals minus mu k mg delta R. And delta R, by the way, is actually the compression of the spring. After all, the spring compresses from its relaxed state, so the block makes contact with the spring, and so here delta R is the distance of the compression, which we are calling x sub c, from the relaxed state to the compressed state. So delta R equals x sub c, and what you see here is that we have a situation in which we have a quadratic. Oh goodness, let's see. 1/2 k x sub c squared plus mu k mg x sub c minus a half mvb squared equals 0. Let's see if we can attach some numbers to this. A half a k will be equal to 25, since k is 50 newtons per meter, so 25 x sub c, and this is gonna, I need to extend the page because x sub c squared plus mu k times mg, I'll let you guys work it out, but should equal 3.92 newtons. We won't put the unit so that we don't have a problem with excess terms, minus 1/2 mvb squared, which we know numerically should be 0.576 equals 0. X sub c, therefore, is equal to, let me extend the page once again, minus b minus 3.92 plus or minus b squared 3.92 squared minus 4a, 25, c minus 0.576 divided by 2a, which is 50. Now, it makes no sense to have a negative compression, and so we discard the negative solution and should then obtain minus 3.92 plus 8.54. Remember, we don't want the negative value because that will give us a negative. And so a negative compression. And so here, when we calculate the numbers, we get x sub c equals 0.924 meters. Well, this concludes the second part of the problem solving session for Chapter 8. In the next part, we will conclude with questions 7, 8, and 9. Until then,